The paper introduces a novel approach to credit card fraud detection using Asexual Reproduction Optimization, ARO, a supervised machine learning method. ARO is based on the concept of asexual reproduction, focusing on sampling from the majority class to enhance classification effectiveness. Compared to artificial immune systems, ICE, ARO significantly reduces training time and increases the recall rate, making it a promising real-time fraud detection system. The importance of fraud detection in the credit card industry is highlighted, emphasizing significant financial loss and reputational damage caused by fraudulent transactions. The authors cite the online fraud report of CyberSource for 2017, revealing that 0.9% of annual e-commerce revenues are lost due to payment frauds through web stores in North America. The paper details the ARO method, explaining its principles and differences from traditional techniques. A comprehensive comparison with ICE is provided, highlighting ARO's advantages in training time and recall rate. The potential of ARO as a real-time fraud detection system is emphasized, offering a promising solution to the challenges faced by banks and card issuers in combating fraud. Credit card fraud is a pervasive issue, affecting 0.8% of online transactions and 0.3% of phone, mail order transactions. The World Bank Group defines fraud as any form of solicitation, bribery, or loan manipulation through misrepresentation. Fraud can be classified into internal and external fraud, with internal fraud involving employee misuse of organizational properties and external fraud encompassing a broader range of activities, including dishonest vendors, untruthful customers, and third-party intellectual property misuse. Credit card fraud techniques have evolved over time, from physical card theft to online fraud, and can be categorized into application fraud and behavioral fraud. Application fraud involves using false information to obtain a new credit card, while behavioral fraud involves illegally obtaining legitimate card information for fraudulent transactions. To combat fraud, protection techniques include prevention and detection systems. Fraud prevention stops fraud from occurring, while fraud detection identifies fraudulent activities after they have penetrated the system. Fraud detection systems can be expert-driven, data-driven, or a combination of both, with expert-driven systems based on fraud scenarios and data-driven methods learning fraud patterns from data streams. The increasing number of credit card transactions has led to a growth in fraudulent activities, making fraud detection systems crucial to prevent significant losses. Effective fraud detection systems must identify a high percentage of fraudulent transactions while minimizing false alarms. Machine learning techniques have been implemented to reduce detection costs, with supervised methods being more common than unsupervised techniques. However, many data mining methods require time-consuming training phases, limiting their applicability. To address this limitation, the authors propose using Asexual Reproduction Optimization, ARO, for fraud detection. The experimental results show that the proposed method achieves reasonable performance on a publicly available dataset. The page discusses various approaches for credit card fraud detection, including supervised and unsupervised machine learning algorithms. It highlights the use of artificial immune systems, ICE, for faster and more accurate fraud detection compared to other state-of-the-art methods. The paper also reviews literature on fraud detection methods, including anomaly-based, misuse-based, and semi-supervised algorithms. It presents a table summarizing different data mining approaches used for credit card fraud detection. Additionally, the overview of credit card fraud detection techniques highlights the effectiveness of artificial immune system, ICE, in optimizing parameters. Association rules are also applied to identify patterns in legitimate transactions and flag those that do not match as fraudulent. Sequential data analysis is discussed, including the use of support vector machines, SVM, and long short-term memory recurrent neural network, LSTM, for modeling time series in fraud detection records, with LSTM proving to be a more suitable classifier. Hidden Markov models, HM, are mentioned for conserving user data and retrieving information efficiently. The use of single-layer feed-forward neural networks for categorizing transactions into 4 groups of low to high risk is also discussed. Improvement of ICE using negative selection and clonal selection is covered, leading to the development of the AISBASED Fraud Detection Model, AFDM, utilizing cloud computing for training. Ensemble decision trees are highlighted for achieving the highest detection rate and reduced processing time. Other approaches include the application of generative adversarial networks, GAN, for generating an augmented dataset to solve the imbalanced dataset problem, a two-stage system consisting of a fuzzy module and a neural network, and the implementation of a customized Bayesian network classifier, BNC. The section also discusses the use of end-to-end neural networks for solving imbalanced dataset and cost evaluation problems, as well as the modeling of credit card transactions using HM and random forest classifiers. Finally, it mentions game theory-based approaches and the use of genetic algorithms to increase the efficiency of neural networks. In the realm of credit card fraud detection systems, the primary goal is to optimize accuracy, speed, and cost. Table 2 presents a comparative analysis of various algorithms, including neural networks, Bayesian networks, support vector machines, k-nearest neighbors, decision trees, fuzzy logic, artificial immune systems, genetic algorithms, and hidden Markov models. This comparison reveals that most algorithms exhibit trade-offs between fraud detection speed, accuracy, and cost, with artificial immune systems, AIS, performing the best. The proposed Asexual Reproduction Optimization (ARO) algorithm is a supervised method for credit card fraud detection, classified as an evolutionary single-objective optimization technique. ARO boasts several advantages over other algorithms, such as faster convergence, lower resource consumption, good exploration and exploitation rates, and no requirement for parameter settings. Furthermore, ARO does not employ selective mechanisms, which can lead to premature convergence. ARO is chosen for comparison with AIS due to its unique characteristics. This paper introduces a novel application of ARO in fraud detection, which has not been explored before. The implementation of ARO involves separating the data into training and testing sets, followed by the application of the ARO algorithm to detect fraud. The AIS algorithm, which has the highest performance, is also briefly explained. The comparison between ARO and AIS is based on their performance on the same dataset. The results of this comparison will provide insights into the effectiveness of ARO in credit card fraud detection and its potential as a viable alternative to AIS. The ARO algorithm, inspired by the budding method of asexual reproduction, is used for detecting frauds in transaction data. It begins by creating two separate matrices for fraud and legal transactions based on the labels provided in the training data. For each feature in the legal matrix, the maximum and minimum values are identified and placed into the maximum and minimum legal matrices. A parent is then created randomly between these values, with its fitness calculated using a specific function. The cut point in the dataset is determined as the best fitness achieved in that dataset. The process is repeated until the parent fit is smaller than the cut point of the dataset. During each iteration, a starting bit, S, and an end, E, are selected within the range of the number of features. The probability of mutation is calculated, and if it is greater than or equal to a random number between 0 and 1, the value of the bit will be mutated. The mutated bud's value is calculated using a fitting function and named as bud fit. The ARO algorithm continues this process to identify potential frauds in the dataset, utilizing the fitting function to evaluate the performance of the parent and bud. This novel approach to fraud detection leverages the principles of asexual reproduction to iteratively refine the model and improve its accuracy. The Asexual Reproduction Optimization (ARO) algorithm is utilized for credit card fraud detection, leveraging the concept of bud reproduction. This process involves fitting a bud to replace its parent if its fitness is superior, repeating until a termination condition is met. Initialization involves a random individual, which through reproduction generates offspring. The best solution survives, and the process continues until a stop condition is reached. In the reproduction stage, a substring is selected for mutation, merged with the parent to form a new individual. The fitness of both the bud and the parent is calculated to choose the best for the next iteration. This process is repeated for all records and features, as illustrated in Figure 1, where each individual is represented as a vector of variables, with each variable being a chromosome. The fitness calculation is influenced by equation 6, which balances exploration and exploitation. The algorithm's performance is monitored through metrics such as equation 5 for the fraudulent matrix and equation 2 for the legal matrix. The bud reproduction process is detailed in Figure 3, showcasing the iterative process of generating superior solutions. By employing the ARROW algorithm, credit card fraud detection can be optimized, providing a novel approach to identifying and mitigating fraudulent transactions. The algorithm's ability to adapt and refine its search through the bud reproduction process enables it to effectively navigate complex datasets, making it a valuable tool in the fight against credit card fraud. The authors introduce the anomaly detection using random oversampling (ARROW) method, which is visualized in Figure 1 as a flowchart. This approach addresses the class imbalance issue inherent in fraud detection datasets, where normal transactions significantly outnumber fraudulent ones. To mitigate this imbalance, ARROW involves random oversampling of the normal class to create a more balanced dataset. The chromosome model used in ARROW is depicted in Figure 2, consisting of an integer part and a decimal part. This model is used to represent the sampled normal records. The authors justify the sampling of only normal records, citing the skewed nature of the dataset, where normal transactions far surpass fraudulent ones in number. This makes the normal record society more suitable for sampling compared to the fraudulent society. In essence, ARROW aims to create a more balanced dataset by oversampling the normal class, thereby improving the performance of anomaly detection algorithms in identifying fraudulent transactions. This approach deviates from traditional methods that focus on undersampling the majority class or oversampling the minority class. By targeting the normal class, ARROW seeks to enhance the detection of anomalies, which are typically rare events in the dataset. Asexual reproduction optimization, inspired by the human immune system, has been successfully applied to credit card fraud detection. This novel approach leverages the concept of bud reproduction, where a larva is generated by randomly selecting values between gene maximums and minimums. The fitness function, a critical component of the ICE algorithm, calculates the difference between a record's distance to normal and fraud transactions. This calculation enables the creation of detectors that identify non-self cells, effectively distinguishing fraudulent transactions. The ARROW method stands out for its efficiency in optimization, offering a distinct advantage over traditional methods. Notably, it eliminates the need for parameter setting, making it a highly versatile tool applicable to a wide range of optimization problems. This adaptability, combined with its optimization prowess, renders ARROW a valuable asset in the fight against credit card fraud. By harnessing the power of ARROW, researchers and practitioners can develop more effective fraud detection systems, ultimately protecting consumers and reducing financial losses. The authors detail the artificial immune system (ICE) approach, a two-stage process comprising negative and clonal selection. In negative selection, lymphocytes are generated through a combination of protein patterns, and those reacting to self cells are eliminated. The remaining lymphocytes undergo clonal selection, where they encounter non-self cells. Lymphocytes reacting to non-self cells survive, protect the body against those cells, and undergo cloning and mutation. The closest colony cells to the non-self cell are chosen as memory cells, reacting to non-self cells like viruses. The ICE algorithm is applied to anomaly detection, where both non-self and self cells are considered as vectors. The training set is normalized, and parameters are initialized. NPOP normal records are selected randomly as primary detectors, and their affinity is calculated using a distance function. NC records with higher affinity are chosen, and a colony is expanded from them. The colony is mutated, and NM of the best mutated population is selected to replicate NM of the worst memory cells. This process continues until a stop condition occurs, with 150 loop repetitions. The ICE algorithm is formally presented in Algorithm 1, outlining the steps for determining NPOP, NC, and NM, and the iterative process of selecting, expanding, mutating, and replacing detectors. The values of NPOP, NC, and NM are set to 25, 7, and 5, respectively, based on previous work by Gotti et al. And Halvaye. The authors then describe the experimental setup, including the dataset and experimental settings, and present the results based on the discussed metrics. The authors evaluate the performance of their credit card fraud detection system using Asexual Reproduction Optimization, ARO, and Artificial Immune System, AIS, on a Brazilian bank's dataset. The dataset comprises 3.74% fraudulent transactions, divided into 9 splits for training and testing, with each split consisting of 70% transactions for training and 30% for testing. The number of fraudulent and legitimate transactions in each split is shown in Table 4. The authors implement ARO and AIS using MATLAB 2016, converting the dataset to CSV format. They train the fraud detection system using both methods and evaluate its performance on the validation data. The performance is measured using 4 parameters: false positive, FP, false negative, FN, true positive, TP, and true negative, TN, which are used to compute 4 metrics: sensitivity, precision, specificity, and accuracy. Training and testing time are also measured, as they are critical issues in fraud detection. To address the dataset's imbalance, the authors use equation 7 to calculate the cost, defined as cost equals 100 times Fn plus 10 times Fp plus Tp, where Fn and Fp are penalized more heavily due to the imbalance. The authors compare the performance of ARO and AIS, with the entire process described in Figure 4. They employ a trial and error method to find the optimal cut points, presented in Table 3, for each dataset. The training datasets contain approximately 28,000 records with 17 features, and the test datasets are used for evaluation. In the testing phase, the ARO or AIS method is applied to the test samples, following the steps outlined above. The ARO fraud detection system integrates a novel algorithm combining anomaly and outlier detection methods. Its performance is compared to the artificial immune system, AIS, method, showcasing improved sensitivity, precision, specificity, accuracy, training time, test time, and cost. Experimental results in Tables 5 and 6 demonstrate the ARO algorithm's superiority. The ROC curve analysis in Figure 5 indicates a 13% increase in the area under the curve, AUC, compared to the AIS method, highlighting its performance in imbalanced datasets. Non-parametric statistical tests, including the Wilcoxon test and Kruskal-Wallis test, further support the ARO model's efficacy. The system's effectiveness is demonstrated through various metrics and statistical tests, emphasizing its potential for practical applications in fraud detection. The implementation of ARO and AIS algorithms for credit card fraud detection is examined in this study. A comparative analysis is conducted across 9 datasets, with the number of fraudulent and legitimate transactions in each dataset presented in Table 4. The ROC curves in Figure 5 illustrate the testing results for both algorithms, demonstrating their performance. The results obtained from implementing ARO and AIS on the datasets are discussed, with metrics for sensitivity, precision, specificity, and accuracy presented in Table 5. The findings show that ARO generally outperforms AIS in terms of sensitivity and accuracy. However, the performance varies across different datasets, suggesting that the choice of algorithm might depend on specific data characteristics. The single-solution evolutionary nature of ARO makes it a faster and more effective method than AIS for detecting credit card fraud. This research contributes to the ongoing efforts to improve fraud detection systems, emphasizing the importance of optimizing algorithms to handle large and complex datasets efficiently. The study highlights the need for continuous evaluation and refinement of fraud detection systems to adapt to evolving fraud patterns and data distributions. The findings of this research underscore the significance of optimizing algorithms to specific data characteristics, paving the way for more effective fraud detection systems. The implementation of adaptive risk optimization, ARO, and adaptive importance sampling, AIS, on various datasets yields notable results, as presented in Table 6. ARO demonstrates distinct advantages over AIS, including significantly faster training times, lower costs, and improved performance metrics such as sensitivity and precision. Across all datasets, ARO exhibits superior performance, with the 9th dataset showcasing the best results, featuring a sensitivity of 0.95 and a cost of $6,407. Notably, the average training time for ARO is a mere 6.25 seconds, rendering it a viable option for real-time fraud detection. The importance of speed and cost in fraud detection cannot be overstated, as efficient algorithms are crucial for effectively handling large datasets. ARO's superiority is particularly significant in this context, as it offers a marked improvement over ICE in terms of training time and cost. The results underscore the potential of ARO as a reliable and efficient method for fraud detection, particularly in high-stakes, time-sensitive applications. By leveraging ARO's advantages, researchers and practitioners can develop more effective fraud detection systems that meet the demands of modern, data-driven environments. The page presents a significant improvement in credit card fraud detection using Asexual Reproduction Optimization, ARO. Notably, ARO enhances sensitivity by up to 25%, precision by up to 56%, reduces cost by up to 41%, and decreases training time by up to 75% compared to previous methods. Table 7 illustrates ARO's superior performance over other algorithms. To validate these findings, nonparametric statistical tests were applied. The Wilcoxon-Sindrank test demonstrated a significant difference between ARO and other algorithms, while the Kruskal-Wallis test confirmed no significant difference between 9 samples. These results suggest that ARO is a promising approach for fraud detection, with potential avenues for further improvement, such as optimizing cut-point values and leveraging cloud computing. The Kruskal-Wallis test compares the performance of the ARO model and the ICE across 9 sections of the dataset, evaluating the equality of results. The test reveals that the ARO model outperforms the ICE in sensitivity, precision, specificity, and accuracy, with significant reductions in training time. This demonstrates the effectiveness of the ARO algorithm in credit card fraud detection, particularly its ability to converge faster to the global optimal point and its robust exploration and exploitation rates. The statistical significance of these results is further supported by the Wilcoxon test, which indicates that the ARO model approaches the significance level compared to the ICE. This highlights the potential of ARO as a superior method for real-time fraud detection systems, leveraging its capacity for rapid convergence and robust exploration. The results suggest that the ARO model can improve the accuracy and efficiency of credit card fraud detection, making it a promising approach for practical applications. The section on future work proposes testing the credit card fraud detection framework based on Asexual Reproduction Optimization, ARO, in a cloud environment, such as Hadoop, for enhanced performance. It also suggests comparing ARO with other optimization techniques like particle swarm optimization, PSEO, and quantum particle swarm optimization, QPSO. Furthermore, the authors emphasize the importance of weighting fields in transactions and using application-based distance functions for each field to increase the model's effectiveness. This approach considers the varying significance of different transaction fields, enhancing the detection accuracy. The paper provides a thorough examination of various machine learning techniques and algorithms employed in credit card fraud detection. It underscores the significance of fraud detection, emphasizing its financial and personal impacts on institutions and individuals. The authors differentiate between transaction fraud, card-not-present fraud, and identity fraud, highlighting their distinct characteristics and challenges. They delve into the application of logistic regression, naive Bayes, KNN, decision trees, random forests, and neural networks for fraud detection. Each model is scrutinized for its strengths and limitations in this context. The paper also explores ensemble learning methods, such as bagging and boosting, which combine multiple models to enhance predictive accuracy. In addition to traditional machine learning approaches, the paper discusses the utilization of deep learning techniques, particularly generative adversarial networks, GANs, to improve fraud detection efficacy. GANs are demonstrated to be effective in generating synthetic data that can augment real-world datasets, enhancing model performance and mitigating overfitting. The authors address the challenges inherent in credit card fraud detection, including class imbalance, data quality issues, and the necessity for continuous model updating to adapt to evolving fraud patterns. To overcome these hurdles, they advocate for the use of specialized databases designed for object-centric process mining, capable of handling large volumes of data and providing insights into complex patterns of behavior. The paper concludes by emphasizing the importance of ongoing research in this field, as fraudsters continually devise new strategies to evade detection. It suggests that future studies should focus on integrating multiple detection techniques, leveraging advanced machine learning models, and utilizing real-time data processing capabilities to enhance the efficiency and effectiveness of fraud detection systems. The comparison of parametric optimization in credit card fraud detection highlights the use of Bayesian and neural networks. Fusion approaches, such as Dempster-Shafer theory and Bayesian learning, are also applied. Optimized light gradient boosting machines are utilized, along with machine learning techniques like decision trees, regression analysis, and hybrid multi-level detection systems. This comprehensive overview showcases the diverse methods explored in credit card fraud detection. This section of the research paper presents a comprehensive review of various machine learning and artificial intelligence techniques applied to credit card fraud detection. The authors discuss numerous studies that utilize different algorithms and methodologies to identify fraudulent transactions. The first set of studies focuses on supervised learning techniques, including decision trees and neural networks, which are evaluated for their performance in detecting fraud. These methods are compared to unsupervised learning approaches, such as clustering and density-based methods, highlighting their strengths and limitations in identifying anomalies. The review also examines the role of ensemble methods in improving fraud detection accuracy, showcasing their potential in enhancing the robustness of detection models. The paper discusses the use of asexual reproduction optimization in detecting credit card fraud. It begins by listing various studies that have utilized different methodologies for this purpose, including genetic algorithms, scatter search, data mining, neural networks, and deep learning techniques. These studies aim to improve the accuracy and efficiency of fraud detection systems. The paper then delves into the specifics of its proposed method, which is based on asexual reproduction optimization. This approach involves generating new candidate solutions through mutation and selection processes, similar to genetic algorithms but without crossover operations. The authors argue that this method can be more effective in certain scenarios due to its ability to maintain diversity within the population of candidate solutions. The paper also explores the application of this method to real-world datasets, demonstrating its potential for enhancing fraud detection capabilities. By employing asexual reproduction optimization, the authors claim that they can achieve higher detection rates and lower false positive rates compared to traditional methods. The research on credit card fraud detection employs various approaches, starting with Gulati et al.'s use of neural networks and geolocation for fraud detection. This is followed by Guo and Li's neural data mining approach. The discussion continues with Kali and Tatavarti's wrapper model and Harris water optimization, as well as Jog and Chandival's system with concept drifts adaptation. Notable papers include Khan et al.'s real-time detection using artificial neural networks and Kim et al.'s neural classifier with a fraud density map. The summary also covers Modi et al.'s web mining-based detection, Patidar and Sharma's neural network approach, and Roy et al.'s deep learning method for detecting fraud in credit card transactions. Additionally, it mentions Saida et al.'s parallel granular neural networks, Lebachat et al.'s deep learning domain adaptation, and Zhang et al.'s novel feature engineering methodology. Credit card fraud detection has been a subject of extensive research, with various approaches being explored to combat this growing concern. One such approach involves the use of probabilistic systems, which have been surveyed to identify their efficacy in detecting fraudulent transactions. Hidden Markov models have also been applied to fraud detection, with studies examining their potential in modeling complex patterns in transactional data. The observation probability of these models has been investigated, with researchers surveying their application in credit card fraud detection. Another angle of research has focused on the application of game theory in managing a pool of rules for fraud detection. This involves strategic decision-making to optimize the detection of fraudulent transactions while minimizing false positives. More recently, model-free optimization algorithms inspired by asexual reproduction have gained attention. These algorithms mimic the process of asexual reproduction, where an individual produces offspring without a mate, to optimize complex problems. Research has demonstrated their applicability in various fields, including credit card fraud detection. These model-free algorithms offer a promising approach to fraud detection, as they can adapt to changing patterns in transactional data without requiring explicit modeling. This property makes them particularly suited to tackling the evolving nature of credit card fraud. Anahita, Farhang, Ghahfarokhi et al. 2023 present a comprehensive study on cost-sensitive modeling of credit card fraud using neural network strategies. The research builds upon the work of Gobadi and Rohani, 2016, who initially proposed this approach. The primary objective is to enhance the accuracy and efficiency of fraud detection models by incorporating cost sensitivity. This is achieved through the implementation of a neural network strategy that takes into account the varying costs associated with different types of errors in fraud detection. The authors discuss the importance of cost sensitivity, highlighting how traditional models often overlook the fact that the cost of false positives, FP, and false negatives, FN, can significantly impact the overall performance. They propose a novel cost-sensitive neural network model that integrates a cost matrix into the learning process, assigning different weights to FP and FN errors based on their respective costs. The model is trained to minimize the expected misclassification cost, optimizing its performance in terms of both accuracy and cost efficiency. The proposed model is evaluated using a real-world dataset, showing it outperforms traditional models in terms of detection rate and cost reduction. Specifically, the model achieves a higher true positive rate while reducing the number of false positives, leading to significant cost savings. The study demonstrates the effectiveness of incorporating cost sensitivity into neural network-based fraud detection models, offering a promising solution for enhancing the efficiency and reliability of credit card fraud detection systems.